Okay, Chem 11, 10 students. Now we're going to move on to part 1B of chapter 8. And this is how we're going to use chemical reaction equations to do various kinds of calculations. All right, so in the first case, we have a balanced equation. We've already set up the stoichiometry properly, and so what we have here is two carbon monoxide molecules reacting with a diatomic oxygen molecule and getting 2 molecules of CO2. And so we can predict how much CO2 we can form if we know how much reactants we have. So in this case, we want to calculate the number of moles of CO2 produced by the complete reaction of 3.82 moles of CO. And so we do dimensional analysis, knowing that those coefficients, there's 2 moles of CO produce 2 moles of CO2. So if we have 3.82 moles of CO and we multiply it by that stoichiometric ratio using those coefficients in the balanced equation, we see that we would get an equivalent number of moles because 2 divided by 2 is 1. So we've got 3.82 moles of CO2. All right, using this same reaction, we can say, well, how many moles of oxygen are needed for a complete reaction of the 3.82 moles of CO? So we do the same kinds of calculation, but our ratio is different because according to our reaction, there is no coefficient in front of the oxygen, so that signifies there is a 1. So it's 1 mole of oxygen to 2 moles of carbon monoxide, and so you're multiplying by 1 over 2 or taking a half of that 3.82, and so you get 1.91 moles of oxygen. All right, so here's another example. So we have this urea, which is a byproduct of protein metabolism. This is in our bodies, and the waste product is formed in the liver and filtered from the blood and excreted in the urine via the kidneys. You can also make it in the laboratory according to this reaction. So what we want to do is calculate the amount of urea that will be produced by the complete reaction of 5.25 moles of ammonia. And so, and then determine the stoichiometric amount of carbon dioxide that it would take to react that 5.25 moles of ammonia. And so on this slide, I'm just keeping track of that reaction. And so if we want to know how many moles of the urea that's produced, we take our moles of ammonia, which has a coefficient of 2. So we put 2 moles of ammonia on the bottom. It produces 1 mole of the urea. And so once again, you're basically dividing by half and you get 2.63 moles of urea that can be produced from 5.25 moles of ammonia. The second question was to determine the stoichiometric amount of CO2 that you would need to react with all of the 5.25 moles of ammonia. And so you take your moles of ammonia, and in this case, it only takes 1 mole of CO2 for every 2 moles of ammonia. And so it requires 2.63 moles of CO2. So we have looked at how much urea we can produce, and we've looked at how much CO2 is required for that reaction. Here's a second one, and I'm going to let you take a little time to look at these, but you have nitrous oxide or laughing gas, and it's an anesthetic used in dentistry, and it's manufactured by heating ammonium nitrate. And here's the balanced reaction for that. And you can see we get N2O as a gas and liquid water. So now we want to calculate the mass of ammonium nitrate that would have to be heated in order to produce 10 grams of nitrous oxide, and then see how much water is also produced. The difference here is that we're given grams, not moles. So, the strategy is to come up with a molar mass of nitrous oxide so that you can convert your mass to moles, because stoichiometric calculations are always done with moles. And it asks you to determine the mass of ammonium nitrate that you would need. So once you get the number of moles of ammonium nitrate, you can convert that to grams. And the same thing with the water. So here's our very first question. We want to get 10 grams of N2O, and we switch that, or we convert that to moles by dividing by the molar mass. Once we know how many moles we're trying to produce, then we use our stoichiometric ratio of the ammonium nitrate to the N2O, which is just 1:1, so it requires the same number of moles. You take that 0.227 moles of ammonium nitrate, multiply it by the molar mass, and you see how many grams it would take to produce 10 grams of nitrous oxide. And so once you've done that, then you want to calculate how much water you would also get. And so you start with the moles of the N2O, and the ratio of water to N2O is 2:1. So you figure out how many moles of water you would produce, multiply it by the molar mass of water, and you see the grams of water you would produce. Okay, another kind of reaction that's extremely important is the limiting reactant, because lots of times in chemistry, one of your reactants is in short supply. It's very expensive, it's very hard to come up with, whatever. And you need to know in any reaction, what your limiting reactant is. So I have a reaction shown here, carbon monoxide with hydrogen gas producing methanol, CH3OH, and we've got a little picture of it. All right, so the other thing you might have besides a limiting reactant is an excess reactant. So that's the one where you have plenty of it, and lots of times that's going to be your less expensive reactant, or easier to come by, something like that. All right, so let's say that we know how much CO we have. We're trying to make methanol. There's a reaction. And we know how much H2 we have, and we want to see how much methanol we can make, but we have to know which is the limiting one, because once it's used up, we can't make any more. So first I ask the question, how many moles of hydrogen are necessary to react with all this CO? We have 5 moles of CO. So we use that stoichiometric ratio of H2 to CO. We want the CO to cancel out, and we want an answer in terms of hydrogen. So it takes 10 moles of hydrogen to react with 5 moles of CO. And then we can look at it the other way. Although it's obvious we don't have enough hydrogen to do that, we can say that for moles of CO, if we have 8 moles of hydrogen, and it's 1 mole of CO for every 2 moles of hydrogen, it would only take 4 moles of CO. Well, we only have 8 moles of hydrogen. We don't have the 10 moles that would be required. So the hydrogen is the limiting reactant. We know we would only need 4 moles of oxygen of CO to react with all the hydrogen we have, and we have 5 moles, so it's the excess reagent. All right, here's another example, and this is Alka-Seltzer tablets, and they tell you it's made of aspirin, sodium bicarbonate, and citric acid. When you put it in water, it fizzes because it produces CO2, which is what the commercials always have. So here's the balanced reaction for that, and what they tell you is an Alka-Seltzer tablet has 1.700 grams of sodium bicarbonate. So this is grams, not moles, and 1 gram of citric acid. And so you want to know which is the limiting reactant, what mass of excess reactant would be left over once you've used up all that limiting one, and what mass of CO2 you can form. And so remember, you have to convert the masses to moles, and then you're going to use that stoichiometric ratio, or they call it a conversion factor here. That's the number of moles. So there's 3 moles of CO2 that you get for every 3 moles of sodium bicarbonate. So it's really a 1-to-1. 3 to 3 is the same thing as 1-to-1. And so you determine the moles of excess reactant remaining and the number of moles of CO2 produced. And once you know how much CO2 is produced, you can convert that to grams. And so here's the math for this. You're starting out with the 1.7 grams of sodium bicarbonate. You see how many moles that is. And you have 1 gram of your citric acid, and you see how many moles that is. And then to determine which is limiting, you calculate the amount of citric acid necessary to react with all of the sodium bicarbonate. You need 0.006745 moles, and that is more than you have, because you only have 1 gram or 0.005205 moles in a tablet. So therefore citric acid is the limiting reactant. And so you can determine the excess of the sodium carbonate, and you do that by comparing the citric acid to the sodium bicarbonate using that stoichiometric ratio. And you see how much would be consumed. You can subtract from the 1.7 and see how much is left, and then convert that to grams. All right, if you want to know how much CO2 is produced, you can take the moles of citric acid, which was 0.005205, use this ratio. There are 3 CO2s for every citric acid from that balanced reaction. So you see how many moles of CO2 you can produce, multiply that by the molar mass, and you see the mass of CO2 which is produced. All right, the last thing we're going to talk about is reaction yield. The theoretical yield is the amount of product that you should get. However, you very seldom get all that. And so there's an actual yield you compare to that theoretical yield, because if you're trying to produce a product, you want your actual yield or your reaction yield to be as high as possible. And the percent yield tells you just how much you're going to get. So you take the actual yield and divide it by the theoretical yield and turn it into a percentage by multiplying by 100. And here's an example with aspirin, which is acetylsalicylic acid. And it tells you how much in the synthesis, how much salicylic acid you would use and how much acetic anhydride. And so it's saying you get 105.6 grams of aspirin. What's the percent yield? And so you convert these to grams, and then you take that mass that you actually get or that you should get and turn it into grams, and you compare it to the 105, and you see it's only a 77.25% yield. Remember that your percent yield should never exceed 100%. If it does, you're measuring something else. All right.